Welcome to Types of Chemical Bonds. So, what is a chemical bond? A chemical bond is a force holding two atoms together that makes them function as a unit. But it's not a physical thing, right? It's just this force pulling them together. And bond energy is the energy required to break a chemical bond. So, we can think of chemical bonds now as an energy. Now, an ionic bond is a chemical bond between a positively charged cation and a negatively charged anion. The ionic compound is a compound composed of a cation and an anion bonded together with an ionic bond. So we can calculate the bond energy for an ionic bond using Coulomb's law. Coulomb's law looks something like this. So we have the energy of that bond is equal to 2.31 times 10 to the minus 19 joules times nanometers multiplied by Q1 times Q2 over R. Now, E is the bond energy, Q1 and Q2 are the charges of the ions, including the sign, so positive or negative, whatever, and R is the distance between the centers of the ions in nanometers, hence why this nanometer is here, to cancel that unit of nanometers there. So, if we look at, say, sodium chloride, the bond length in solid sodium chloride is 0.276 nanometers. So the bond energy then is this quantity 2.31 times 10 to the minus 19th joule nanometers times plus 1 from the charge of sodium times minus 1 of the charge of chloride divided by the distance between them, R, so the 0.276 nanometers, and that is equal to minus 8.37 times 10 to the minus 19th joules. So the negative sign here indicates the bond is an attractive instead of a repulsive force. Note that it is possible to get a repulsive force if we take, say, chloride with a charge of minus 1 and, say, fluoride with a charge of minus 1. Well, now we'll have a negative times a negative, so a positive value. That will give us a positive energy. That means that forming a bond between a chloride and a fluoride ion, that gives us, well, it requires energy. We have to put in energy. A positive energy means energy that we have to put in. A negative energy means energy we can get out. So with sodium chloride, we get out energy. Energy change is negative. With two ions of the same charge, either positive or negative, or like sign charges at least, those will have a chemical bond energy of a positive value, which means basically it will spontaneously, those ions will spontaneously repel each other and the bond will spontaneously break. So suppose we have two hydrogen atoms at some distance from each other. Now we're going to look at a chemical covalent bond. So if we have one atom over there and one atom over here, each atom has one proton in the nucleus, one electron orbiting the nucleus somewhere, but that electron is relatively close to the nucleus, at least as far as the scale. So we have our two atoms really far apart. As we get our atoms closer together, the nucleus of one atom starts attracting the electron of the other atom. So this electron begins to be attracted to that nucleus. That proton is also, that nucleus is also attracted to the electron. This electron is also attracted to that nucleus there. This nucleus is also attracted to that electron. And so now we have three types of forces involved. We have proton-electron interactions, so between the nuclei and each of the electrons. So between this proton and that electron and this electron, and between this nucleus and that electron, and between that nucleus and this electron. So those are attractive forces. Those are pulling the electrons towards this nucleus and towards that nucleus. We also have proton-proton interactions. This is a repulsive force. So this is a force that's pushing outwards against the two nuclei. It's trying to push the two nuclei apart because this is a positive charge, that's a positive charge. They want to tend to move away from each other. And we also have electron-electron interactions. These are repulsive forces. So this electron is repelling that electron. So as we get our atoms even closer together, these atoms will bond if the proton-electron attraction, if those attractive forces are stronger than the sum of the proton-proton repulsion and the electron-electron repulsion. If the repulsions are stronger, then the atoms don't bond. If the attraction is stronger, then the atoms do bond. So hydrogen atoms will bond, so that means that attraction force must be more prevalent, or more stronger. So the hydrogen atoms at a distance of 0.074 nanometers have a strong proton-electron attraction and relatively weak repulsion, so the hydrogen atoms form a chemical bond. So by getting our atoms very close together, we keep our nuclei still far enough apart that they're not repelling each other too badly, but we get our nuclei close enough to the other electron that it's attracting a good bit, but we're also able to keep our electrons far enough apart from each other that they're not repelling each other too bad. So, as the nuclei of our hydrogen atoms get very, very close together, then the repulsion of the protons becomes very, very high, and then that will tend to push our atoms farther apart. So, there's something pulling our atoms together. That's the attraction of the protons in one nucleus for the electrons on the other atom. Those are pulling our two atoms together. But there's also a force pushing them apart, which is the repulsion of the two nuclei for each other. And so there's sort of a sweet spot in between. And so there's this region of stability where the hydrogen nuclei are sort of a moderate distance from each other. So not too close, not too far apart. And so we can see that sort of pictorially here and graphically over here. So as we have our atoms very far apart, the two electron clouds are largely undisturbed. As we move them closer together, you can see they're sort of merging in between. There's now more electron density in between. And as we get them even closer, there's now a lot of electron density in between. This is the force that's pulling those nuclei together, right? Because the nucleus on the right sees the majority of the electron density on the left, so most of the negative charge is over here, so that nucleus wants to tend to move this way towards that negative charge. This nucleus sees the opposite. It sees more of the electron density on the right side of this nucleus, and that means it will tend to try to move to the right, except that will eventually balance out with the repulsion between those two nuclei. So they get to the point where that attraction and repulsion are balancing out, so there's no net force. And it's the same thing we see in here. So when we start out with, so here we have the internuclear distance on this axis and the energy associated with it. We start out with our nuclei really far apart. Our two atoms are very far apart. The energy there is 0. We're very close to it. As we get them closer together, now that attraction force becomes significant and the energy starts to drop. At some point we get to the energy minimum. At this point now, that repulsive force between the nuclei is exactly balancing the attraction force between the nuclei and the electrons. And then as we try to push our nuclei closer together, now they're saying, no, that's not going to happen, and they repel more and more and more until we get up to this point at which the repulsion is strong enough to now to completely dominate the interactions, and those hydrogen nuclei will tend to fly apart. Now they won't really fly apart because they'll come back down into this zone that will tend to pull them back together. So that 0 point of energy is defined with the atoms at infinite separation, really, really far apart. Essentially no interactions between them. At very, very short distances, the energy rises very steeply because of the repulsive force between the nuclei. This is the sort of very, very strong force that has to be overcome for a nuclear fusion to occur. So in our sun, for example, we have two hydrogen nuclei that get fused together to form a helium nucleus, and we have to overcome that force, which is why it doesn't occur in, say, the Earth's atmosphere. We have to get those two nuclei so incredibly close together, we basically have to really slam them together to get over that wall, that repulsive force of those two nuclei being close together, those two protons being close. So the bond length is the distance at which our system has a minimum in energy. That's the point at which the repulsive and attractive forces are totally balancing each other out. So the molecule is more stable than the two individual atoms by whatever the bond energy is. So if the bond energy is negative, then it's more stable. If the bond energy is positive, then it's less stable, and the molecule will spontaneously fly apart. So to break the bond, That means we have to separate the atoms to infinite distance. So we have to, in order to pull apart two hydrogen atoms that are bonded together, we have to put in energy, we have to do some work to pull those atoms apart against that attractive force keeping them together, just like trying to pull apart two magnets. So this type of bond is called a covalent bond because those electrons get shared in between the two atoms. So if the two atoms are not identical, as they were in hydrogen, then they form a polar covalent bond. So one of the atoms is a little bit stronger than the other, its electronegativity is higher, it's going to pull on those electrons and pull it towards itself more strongly than the other atom will. So in this case, in a polar covalent bond, the electrons are shared unequally. They're still shared, but they're shared unequally. One of them has the electron density more than 50% of the time, basically. It has more than 50% of the electron density. But it's not totally stripping the electron away from the other atom like it would in an ionic bond. So the atom that's more electronegative has a greater share of the electron density and becomes slightly negatively charged. The atom that is less electronegative has a lesser share of the electron density and becomes more positively charged, slightly positively charged, but not total. So something like HF, hydrogen fluoride, is a polar covalent molecule. So the hydrogen is slightly positively charged because, of course, fluorine has the highest electronegativity of all the elements. And so the electron density tends to be more towards the fluorine side because the fluorine is pulling on those electrons more tightly. And so what we end up happening is we have a slight positive charge on the hydrogen side of the molecule and a slight negative charge on the fluorine side of the molecule. And we have two different ways of demonstrating or displaying what that separation of charge. So one way is by having this little lowercase delta. That's the Greek letter. It's similar to D. So we have the delta plus for a slight positive charge or partial positive charge, and a delta minus for a slight negative or partial negative charge over on the fluorine end. The other way to do it is by drawing this arrow, where we have the arrow pointing towards which direction the electrons are going, the negative end of the molecule, and then a plus on the tail of the arrow showing which is the positive side. So that's the side where the electrons have left from, giving it the positive charge, partial positive charge at least. So note that polar covalent molecule, apolar covalent molecule has some ionic character due to the attraction of the slightly positive ion atom to the slightly negative atom. So there's not really a clear distinction between ionic compounds and covalent compounds. There's really a spectrum between totally ionic and totally covalent. So really what we have is bonds that are totally equally, where the electrons are totally equally shared, and a gradient through unequal sharing, more unequal sharing, really unequal sharing, and then not sharing at all. One of the atoms is strong enough to just totally strip the electron away, and now we have two ions, where one of the atoms has lost an electron and the other atom has gained an electron. And so with an electronegativity difference of 0, we have a totally nonpolar bond, covalent bond. Up until an electronegativity difference of about 1.7, it's a polar covalent bond. Once we get over an electronegativity of around 1.7, now it's really an ionic bond. The character of the bond really is ionic. So that was types of chemical bonds.